Welcome to the Startup Competitors Podcast, where we talk with early-stage entrepreneurs to understand what information they use to inform product roadmap, strategy, and market differentiation.
Welcome to the podcast. Today we have Ian Hamilton, who's the CEO of Atlas Energy Systems. Ian, welcome.
Awesome. Thank you, Michael. And thanks for having me on the podcast today. Yes, as Michael introduced, I am CEO of my startup company, Atlas Energy Systems. We are an early stage energy technology company. We're playing around with the idea of calling it like industrial hard tech. Basically, what we do is we are engineering, designing, and working with manufacturers to make technology that directly converts heat into electricity with no moving parts. The core technology is actually called thermionic energy conversion. It was developed very heavily in the 1950s, 60s, 70s, and 80s by NASA and the Soviet Union. It was actually flown in 2 operational nuclear reactors in space by the Soviet Union. The core advantage of this was that there are no moving parts, so it can survive the G-forces of liftoff and re-entry. It's incredibly robust and actually fairly efficient when compared to some other similar technologies, around 10 to 15%, some models actually breaking the 20% mark. Luckily for us, as the startup company here, one of the big things back in the day was that the technology itself was not economically viable, even though it was physically viable. So a lot of your primary designs were, they had the budget of NASA and were part of an actual nuclear reactor. So we're talking precision machined tungsten tubes and things like that, even basic prototypes costing hundreds of thousands of dollars. So where we come in as a company, and where I got my start, I have a background in nuclear engineering and materials science, both from Purdue University, where I learned about this technology and thought, hey, this works in general. Why don't we try and make it manufacturable? So where we come in is basically redesigning the core physics that's been proven, and we know the core materials to use, but how do you redesign it into a form factor that we can make thousands at a time, basically for $100 each instead of hundreds of thousands of dollars each. So that's our current basis for the core technology, and where we're applying this to is actually in remote power generation in the oil and gas industry, where we've gotten a lot of interest from customers. But this is simply just kind of the lowest hanging fruit for our entry market. The core technology itself is actually really interesting in that it's agnostic to the type of heat source that you use. So the technology, like as said before, has actually been used in nuclear systems, combustion-fired systems, and even concentrated solar power as well, all tested and built there. So it's actually more of a platform, and we actually have a very large total addressable market that we could hit as we move forward. But like I said, we are pretty focused on our entry market and have our customer basis set up and our go-to-market strategy for the oil and gas industry, which is where we're deploying the technology first.
Killer pitch. And you are the first nuclear engineer I believe we've had on the podcast. So welcome. Let's go to current status. Paint a picture of where you and the team are on the bell curve of outcomes. Are you still 2 folks in a garage? Are you have a full team of 50 people rocking and rolling? Where are you at? Any vanity metrics you can share at all?
We are slightly further along than in the garage. We have our own manufacturing space and office space. We're currently based out of Romeoville, Illinois, but we're actually looking to relocate the company for other reasons up to the Pacific Northwest. There's currently 4 of us. I started the company as an undergrad at Purdue University in materials science. It showed some merit with the concept and got my master's degree in nuclear engineering there as well. Got into the Argonne National Lab Chain Reaction Innovations Program, which is what brought me up to Lamont, Illinois, where basically we got almost $1 million from the Department of Energy to prove out some of our concepts for the thermionics, and where I brought on my first employee, Nisarg Patel, who has a master's in nuclear engineering as well. We basically proved out the technology as much as we could with a demonstration and a prototype, kind of just to show the operation. The whole point of the Argonne program that we were in was specifically to kind of get you over that valley of death, or at least help with it. It did that a little bit, at least to the point where we are starting our fundraising, our seed round of actually equity-based fundraising. And we, to do that, brought on a CFO, Scott Noble, who's got an MBA from Notre Dame. And then to help out more with the technical side, we've got a research professor at Purdue University, Kazuaki Yazawa, that's an expert in thermal energy management and power generation. So that was the team. We kind of set all that up around June, July-ish, and then we've been working on our current seed round of fundraising for about the past 6 months now. We are coming in and closing the first tranche of that, about the first half of our $1.1 million raise. We have a lead investor, Vision Tech Partners, based out of Indianapolis, Indiana, that set the terms with a $4 million pre-money valuation. And so you can do the math on how much equity that takes and whatnot. So we are getting ready to close basically the first half of it, but we are still looking for investment on essentially the second half of the round. So that's where we're at financially, and with the team. The technology is always an interesting question. Like I said, we've done some non-trivial experimentation and development, design and engineering on our own, but at the end of the day, all we've really done is kind of proven out a new design or a manufacturing process with some of our partners. Our budget on that has only been maybe $200,000. So actually, we haven't had too much resources for technology development there. But one of the interesting things that we get to do is take advantage of the basically 4 decades worth of government funding that went into thermionics, by some estimates over $100 million worth of development. So we are at, if you're familiar with the technology readiness levels, we personally as the company are probably around 3 or 4, but the core technology itself has actually, like I said, been flown in space in operational nuclear reactors. And that's closer to 6, 7, maybe even 8. So we're really trying to leverage a lot of the history and the core technology there, so that we don't have to raise $100 million ourselves for product development or anything like that. We get to take advantage of a lot of the prior research and history of the core technology itself.
All right. I have so many questions before we go into the competition stuff. Just about the path that you've been on. First, I feel like I should make the quick disclaimer: this is not an offer to invest. No solicitation is being made of our listeners to invest. But tell me, so when I think of that time that you spent working on the proof of concept at what lab was that?
Argonne National Lab, up here in Lamont, Illinois.
Okay, perfect. So when you were working at Argonne National Lab doing that proof of concept, what does that look like for something like this? And what does success mean? Is it just that you can, you built a physical piece of hardware that converts heat into energy in the way that you want it, and then it's around to high fives and you go crack some beers? Or are you showing that to somebody for commercialization? Are you leveraging that for patents? This is so different than software. I'm fascinated at how does that all work? What were you trying to accomplish in there? And then what did success look like?
Yeah, and that's a great question, and basically your first part is essentially what we were going for. So there is, and some of your listeners might be able to look it up. If you just go to YouTube and look up thermionic energy conversion, there's a black and white YouTube video from GE Research from the 1960s, where he basically took a blowtorch onto a thermionic energy converter and generated enough power to do a fan. That was the last probably working combustion-fired thermionic converter from 1960. So our main goal was to, one, get back to that place and rebuild an operational device, and then two, use what we learn in that building of the device to design something that's going to be mass manufacturable, and specifically the process of doing so. We were actually the first people to build a standalone combustion-fired thermionic energy converter to produce net positive power, very small amount of power, only a couple milliwatts, only enough to light up like a LED light bulb or whatnot. But we were the first people to do anything like that, and as far as we can tell, over like 50 years. That was kind of our first step, our big milestone. We've got a video of it. It's looks very large and expensive because it was. And so our next step was, okay, well, how do we take this core design and turn it into something much smaller and simpler so that we can actually manufacture it? And one of the big problems with all of this is that the core technology operates using a hermetically sealed cavity that has to have metal bonded to ceramic, which have much different coefficients of thermal expansion, and this device is going to be operating at high temperature. So one, that is a huge engineering problem and task that we've been working on for our design, and that's kind of the first thing that we solved for our manufacturing process and our designs. The second thing was that the active ingredient on the inside of this hermetically sealed device is cesium metal, and it adds beneficial properties to the electrodes, as well as allowing the electrons to traverse through it from one side to the other side. And basically, that's good and all, but cesium is highly reactive to oxygen, so you can only do this under high vacuum. So this poses a very interesting manufacturing process where you have to assemble this entire device and technology without it ever touching oxygen, all the way from like cracking open the glass cesium vial that you can order online to actually getting it into a high temperature vacuum brazing oven.
And you did this all while you're at the lab? Like, so you guys did this manually, and then later you have to develop a manufacturing process to do this at scale?
Yes, basically. So we started out developing this at the lab with some of their partners there. It was a great program. We loved the support. However, one of the big takeaways from it is that it's a government-run institution, a lot of paperwork and bureaucracy. So developing a quick experiment or something to run very quickly was not exactly a huge option. So actually, we took all of our development off-site, around 10 minutes down the road in Romeoville, Illinois, where we basically built our own manufacturing facility. We got mini CNC machines and built our own vacuum brazing oven. So we were able to develop this process, basically, like you said, manually, just one or two things at a time. And then all we're doing is partnering with a manufacturing partner that just has much bigger vacuum brazing ovens to develop our process with and actually use their equipment. So that was the main goal, kind of the main breakthrough, our quote unquote secret sauce that we have patents pending for, and probably many more to come, was actually how do you get this reactive metal inside this hermetically sealed device at scale and cost effectively. So that was our primary goal that we set out to do. And as far as we know, we have done that. It's verified by some of our manufacturing partners that agreed, yes, this is the way that you should do this, and we can do it. So that was exciting to work with them on.
So then success coming out of that program at the lab is you have a functioning proof of concept that you can show people in the sales cycle. You have provisional patents for, obviously for how this process works at scale, and you can leverage all of that to go out and raise funds and start to take the next steps, right?
Exactly. Yep. Yeah, I think Going into the program at Argonne, we had grand visions and all kinds of different things that would have qualified for success. But I think at the end of the day, the path that we chose for this development plan, basically it gave us about a year and a half to work on this process, figure out the materials, physical design, and things like that. And yes, we have a physical proof of concept basically that we manufactured. And then we developed the process and provisionally patented around that. And so that was kind of our success throughout the program.
So now this next question is going to be a super naive one because I'm not sure I fully understand the places or ways that you would leverage a technology like this. But there's a core question in here somewhere around like, how do the economics of this work, right? Because if I'm trying to produce energy in this way, I'm trying to balance what's the cost of energy via some other method versus the cost of buying this product, right? And then at some point you reach a payback period, right? So talk a little bit about that. How much of people using a solution like this, is it about that just basic economic cost of this energy versus energy from another source versus maybe in the applications, I'm trying to think of how you could apply this in oil and gas, right? Maybe in the applications where you're using this, it's the only way to get energy because you're out in the middle of nowhere and there's, it's not like you can just pull from an outlet or something like that.
Yep, and that's you hit the nail on the head. The easiest place to start is where the availability of energy is drastically reduced or non-existent. So the ideal case for this and kind of the biggest selling point is actually not cost, not efficiency, but it is robustness and reliability. So in the oil and gas industry, they currently use thermoelectric power generation for things like cathodic protection, powering pumps, sensors, lights, all kinds of different equipment where basically they siphon off a combustible material, most likely natural gas, burn it, it heats up a thermoelectric module, which I won't go into that here, but you can look up how they work. And that generates electricity from heat with no moving parts. So basically a very similar model or technology to what we're doing, except that core technology is incredibly expensive, incredibly inefficient, which, as I just mentioned, those are the two things that they don't really care about. One of the big things that they care about is robustness and reliability. And thermoelectrics have a tendency to burn out at unexpected times. We've talked with customers and sales partners that have had devices last as long as 10 years, and then they've had ones that have burned out in under a month. And these things are in the middle of nowhere, and their sole job is to work nonstop for power generation. So basically what we have come up with is we're partnering with a sales and distribution team that actually used to sell these thermoelectric boxes to the oil and gas industry, and basically working with them to develop a new product that will just simply be a one-to-one swap, just a straight-out swap of their current product, so that if you're the customer in the oil and gas industry, what you see is the same sales guy that sold you the same technology that you're used to 2 months ago, but here he's rolling up to the oil field. In the back of his pickup is a box that looks very similar to what you're used to buying, but in fact it actually has a different core technology on the inside that is less expensive, more efficient, and most importantly, drastically more reliable, because thermionics do not suffer from burnout due to temperature fluctuations as thermoelectrics do. So we believe, because of all those factors, we have a very good go-to-market strategy with this technology. Another example of kind of a use case, like I said, with the nonstop or reliable power generation, the easiest one to think about is kind of like a backup generator or something like that for homes. There's a big influx in development for natural gas turbines for power generation or backup generation for business or homes or hospitals or whatnot. One of the interesting things about them is that sometimes they're actually so loud that they violate city ordinances on noise, so you can't actually place them where you want to. Our device, even though it would be less efficient, would cost about the same or less, but would be silent and would be ready to go whenever you need to turn it on. Another big application is actually for remote power generation for the telecom industry. So remote cell towers and cell towers in general have to have a 99.925% uptime, which means they can only go down around a half an hour every month. Right now in remote locations, they're either powered via diesel generators or natural gas generators that need maintenance every 36 to 60 days. And when they maintain them, they actually have to cut the power to it, and the cell tower goes down for hours, if not days at a time. And so then they violate their service life agreements. There are a lot of niche applications like that where we can kind of come in. Again, we don't have to hit amazing efficiency marks right off the bat, and the economic points are much easier to hit from our manufacturing process. And then as we scale up, get into those early markets, then we can worry about, okay, how does this look cost effective wise, techno-economics of using concentrated solar and doing a 100 megawatt concentrated solar thermionic plant or something like that. So we're not going to worry about those very strict economic factors until much later down the road, because we have a lot of potential entry markets where we can hit those pain points very early on without too much design changes on our end.
How did you find and get partnered with that sales and distribution team that you're working with?
They contacted us. We have only ever had inbound interest because this problem is so large and such a big pain point for like the past 30 years. They actually contacted me through just my LinkedIn profile, asking if our technology could be a one-to-one swap of the incumbent technology. We've been contacted by giants like NG and Repsol. That's $100 billion worth of natural gas company right there that are specifically have an eye out for thermionics, thermophotovoltaics, thermoelectric advances in those technologies, heat to power, no moving parts things. So we get contacted either through my LinkedIn or our websites from prospective either customers or partners about once a month, maybe even more frequently than that. Most of the questions are, hey, when is this ready? When can I just buy this off of Amazon? And we say, hold on, give us a little bit. We're scaling up right now. So like I said, we've only ever had inbound interest, which bodes well for when we actually do hire a business development person and work on our own marketing and sales for the technology ourselves.
Got it.
This episode is brought to you by Full Stack PEO. Most founders start companies because they figured out a better way to solve a problem or serve a need, not because they love tracking payroll, filling out compliance forms, and explaining employee benefits packages. And yet, all that stuff still has to be done. That's why there's Full Stack PEO. Full Stack PEO specializes in turnkey HR for emerging companies, not just those core services, but advice and expertise that help founders maximize employee potential. Curious? Find out more at fullstackpeo.com.
All right, let's switch gears. When you think about competitors in the space, who or what comes to mind?
Yeah, of course. Obviously, after that whole about 10-minute spiel there, our biggest competitor is kind of the incumbent technology, the thermoelectrics. That's what we're trying to hit and target right now. There are other competitors both in the core technology itself. We are one of 3 thermionic energy converter companies that are in operation right now. So there's another company called Spark Thermionics. They were actually got their start through the same program that I got in for Argonne, except their program was out at Lawrence Berkeley Lab out in California. And then another company that is working on this is called Modern Electron. They've raised quite a bit of money through some of their high-profile connections doing thermionic energy conversion as well. So we're not the only ones in this space for the core thermionic technology, but because of our simple go-to-market strategy and manufacturing plan, we think we'll be probably the first to get to market. And again, once we get to market, our main competitor is actually thermoelectrics, which we stand up pretty well against. As we get to any larger power scales or different use cases, our main competitors are going to be Stirling engines, natural gas generators, or diesel generators. And then we really have to start working on the unit economics and the efficiency to kind of compete on some of those spaces. But those are the core technologies that we are basically mainly competing with. Not to say that the manufacturers of those core technologies aren't interested in not being a competitor, but being a partner. We recently, through a manufacturing expo day, got some interest from Cummins because they're trying to expand their power generation capabilities, even though they're one of the larger diesel generator manufacturers in the world. So there's definitely a lot of niche places where we can fit in, so that if there is a large market incumbent like CAT or Cummins or something like that, maybe we don't try and compete with them directly, but actually try and partner with them. And so then our true competitors are either on similar power generation technologies or actually identical thermionic competing companies, which are, again, two other startups right now.
So you remember the disclaimer before we started where I said I'm potentially going to ask you a question that you probably don't want to answer and you're allowed to say pass?
Yes.
Here's one of those questions. Like, I have to believe at the space that you're playing in with the competitors that you just rattled off, what at scale, right? The competitors at scale that you just rattled off, GE, Cummins, CAT, like, how long do you remain an independent entity before this just gets acquired and pulled into one of those larger companies and commercialized there?
That is a great question. A lot of our projections are not very long, is the answer. Actually, Schlumberger Limited is one of the most prolific acquirers of startup companies in the oil and gas space and power generation space. Actually, in 2016, they led a $23.5 million Series C round in a thermoelectric company to develop thermoelectrics for oil and gas power generation even further. So yes, we don't want to, again, be overconfident or anything like that, or put ourselves out there, but we believe that we'll get some pretty significant attention from the big players, GE Oil and Gas, Schlumberger, things like that, within probably the first couple of years in being into the market, which the going rate of acquisition in the oil and gas company space is like 12x EBITDA, yields a fairly good return rate for our seed round investors, which obviously they want to hear.
Right. That's fantastic. The Spark and the Electron.
Modern Electron.
Modern Electron, thanks. Are they also launching in the oil and gas space, or are they launching in different verticals?
So they've got different verticals. They're both pursuing different variants of the core technology. Spark Thermionics is trying to take advantage of the advent of like MEMS manufacturing and silicon etching and things like that for actually nano-based devices. Their technology is very tiny for energy harvesting, very small power generation for sensors on the order of milliwatts and things like that. Actually, all of their funding has come for DoD applications. So sensors on hypersonic vehicles or engines and things like that. So that's kind of where I think their space is. And then Modern Electron, one of our other competitors, one of their big reason they have raised so much money was they are going after actually the combined heat and power and like topping cycle market, which goes for a very good Silicon Valley investor pitch when you think about even at 10% efficiency, a 10% efficiency increase of every gas turbine generation in the world, well, that's like $120 billion right there. I think that's kind of the market vertical that they're looking at as their space. And we would like to get to those ideas and that concept as well. We just think that the remote power for the oil and gas is a much lower hanging fruit. And again, we've gotten a lot of inbound interest for that specific application. So even though they are direct competitors in core technology, the thermionics, we're all kind of going after our own little subsections of the potential markets.
Yeah. Which is super interesting that you would all look at those markets in such a different way, right?
Yeah.
And in terms of where to start. What drove you? Was it just the inbound leads that drove you to oil and gas, or was there something else there that, you also said kind of low hanging fruit. Was it low hanging fruit because of the technology need, or just because you already had the contacts reaching out to you there?
Actually, yes, both. How we originally got our start and got to where we are was, again, I learned about all of this in my master's degree at Purdue in nuclear engineering. We were specifically designing all of these for actually nuclear applications, and that's where, if you look up my Forbes 30 under 30 profile for 2018, it talks about using radioactive waste or spent nuclear fuel for power generation. So we were talking pretty heavily with NASA and the Navy and got a lot of interest with them for nuclear power development, going back to the roots of the core technology. Again, it was used in nuclear reactors in space. We very quickly found out that development timeline is on the 20 to 50 years, and we would probably have to raise at least $100 million to be competitive there. Kind of via serendipity, right around that time, we started getting inbound interest from the oil and gas industry that they were perfectly fine with 5 to 10% conversion efficient. And the deep pockets of oil and gas didn't really mean cost was a immediate prohibitive factor. And so when our first people asked us if we could make like a 1 watt device, a simple thing the size of a quarter, we said, yeah, that's something that we could look into and do. And they said, okay, well, what if we wanted 100 kilowatts? And we said, oh, I don't know about that. And they said, okay, that's fine. We'll just take 100,000 1 watt devices and string them together. Can we have 100,000 devices? To which we said, no, we're going to have to work on that. And so that's kind of where our market need / pivot came from about a little over a year ago, when we were most primarily focused on nuclear stuff and just the like I said, the low-hanging fruit, the ease of the technology to solve these problems in the oil and gas industry with very little change to our core ideas at a much expedited timeline worth of development and revenue generation. It was kind of a no-brainer to make that switch.
That's awesome. Switch gears for me a little bit. I want to, because there's an obvious answer to this question if this takes into account the trajectory of the company overall, but I'm more interested in you personally. So a little introspection on this one. What's been your biggest challenge that you faced to date going down this path since you guys originally came up with the idea and said, hey, we're going to go into the lab and do this? And your answer can't be figuring out the manufacturing process and the 6 months that it took to do that. I already know that was hard. So just you personally, what's been either the biggest pain point, thing you've had to learn, obstacle you've had to overcome going down the path of launching this company?
Yeah, of course. And that is actually a pretty easy answer. Explaining it to people. We have had all kinds of varied interactions with either investors or customers. Actually, one of our, even very early on, we won second place at the Purdue Burton Morgan Business Plan competition when I was an undergrad. And one of the judges, we found out later on, was a Siemens Energy Technology Scout. And we found out that the reason we got second place was because she derailed us from getting first place, because her job was to keep an eye out for new, exciting, different technologies. And because she'd never heard of this, she just outright did not believe it was even physically possible. And so during the judging session, she told everyone that, no, this is not possible. This is not a real thing. Meanwhile, all the other judges thought to just simply Google it and realize that it was an actual thing, which is why we still got to be second place. But yes, it's definitely been conveying not only the technology, but the value proposition. I'm actually surprised you have not asked the question of the, why hasn't this been done before type of thing. We get that a whole bunch, mostly skeptics, which is very surprising given like I said, the track record with the technology. We didn't invent the core science. We're just changing and inventing the manufacturing process. But you'd have no idea how many people just pass it up immediately and think that it's black magic or doesn't exist and it's not a real thing. So definitely finding the key way to explain it in a way that people can understand it easily and really convey it in a good value proposition way, specifically for investors, but also in partners and things like that as well. Definitely conveying the core technology message, because we've even tried strategies about telling people, don't worry, it's just a black box. All you got to do is get it hot and it produces electricity. And then we go over the market and the financials and whatnot. They all get that. But at the end of the day, they want to know how it actually works and what's going on the inside. And then we lose everyone at that point. So we found, I keep a running total in my head. The average investor takes about 2 months to fully grasp the concept if they have not actually heard of the technology before. So that's been my personal biggest problem so far.
Interesting. And I can make an intro if you want. I gotta introduce you to Scott Massey if you've not met him.
Oh yeah. I know Scott very well. We've talked a lot.
So he is the single, like, out of I've done 100 of these podcasts now. Scott's description of how helioponics works, it like is the most like articulate, break it down for you in such a simple way, like description of a technology I think I've ever heard. Like he's so good at that piece in particular, right? Of like what's inside the black box. Now, arguably, I suspect your black box is a lot more complicated than his, but he's really good at that. If I gave you the challenge, describe what thermionics is for my 9-year-old, what would you say?
Yeah, of course. And actually, I was going to say I have that pitch ready to go, because that's basically how I've had to start describing it. So at its core, you have 2 electrodes, 2 pieces of metal that are separated from each other. You get one so hot that it actually boils off its electrons, just like boiling water on your stove. Those electrons can then hop from one piece of metal to the other one. Now you have more electrons on one side than you do on the other side, and the only way for them to get back is to flow through a load, like a light bulb, and it looks like a heat-powered DC battery. So all you're using is heat to transfer electrons from one side to the other side, and they literally just hop across, and that's all it is.
So good. That was well done. I wish I had an audience applause button for you. That was really good. I totally tracked it. All right. Okay. What do you think is going to be the next big challenge as you go to scale? What's the next obstacle you think that you and the team need to overcome? And then follow up, how are you preparing for that?
Yeah, so the biggest thing is going to scale and in the actual manufacturing. Luckily, we have identified a really good manufacturing partner for all of this, and we're working with them, and they're experienced in manufacturing technologies like this, not this specific one. So our plan is to work with them over the next couple of months.
Real quick, how did you identify them? Did they reach out to you as well, or did you go hunt them down?
Hunted like crazy. We had to search through dozens of potential manufacturers that could actually work in this space. Again, one of the big things is you have to hermetically seal a metal to a ceramic, which is a non-trivial task. However, there are companies that do it. And so we had to find the right one that was willing to work with us. Basically everything from prototyping and product development, making 2 or 3 at a time, all the way up to, hey, we need hundreds a week. And so I think that's actually the biggest hurdle, the biggest process and step is we're very confident on the first 10, and then even probably the next couple dozen or even 100. But at some point, we might get to volume levels where we're going to have to work with our contract manufacturer to build out a second production floor, and they're going to have to start ordering more equipment to physically meet our
Oh,
capacity
wow.
and things
Yeah.
like that.
Interesting.
So that's going to be probably the biggest thing, and they're definitely open and excited to working with us, especially since they mostly do high cost, low volume stuff right now. A lot of military and defense things, biomedical stuff, and I think they're kind of scared and excited that at scale or at volume, we very well might be like 80% of their production capacity at any given one time for one product line. They're excited to work with us, but I think that's going to be the next biggest hurdle. And one of the key things that, again, we've done that kind of was never done in the past was, instead of designing a device, a thermionic energy converter that we will know will work and it's going to be optimized and awesome, well, if you take that to a manufacturer and they say there's no way we could make that, let alone 100 of them or 100,000 of them, then you wasted your time in the first place. So we've been working with them very intimately, going back and forth on different designs, and actually the processes on how you actually specifically design for scale manufacturing, which is unlike anything that's been done before for the core technology. So that's another unique aspect that we kind of bring to this. So I think that's going to be the biggest hurdle and biggest process and project moving forward.
And when you went to find that manufacturer, is that starts with Google searching, then you're smiling and dialing, and then once you find a few that claim they can do it, you're just doing site visits to ferret that out? Is that?
Yep, that is how it was.
Right.
Started with Google searching, found a couple, called them. There was a lot of people that had the expertise but didn't work in this kind of size, shape, unit economic space. So we found a company that had all the expertise, the tooling, the know-how out in Maryland, but they braze together and manufacture like 3 aircraft engines a year. That's their bread and butter. 10,000 little devices, the smaller than a softball, was not what they were prepared to do. Things like that was, we had to find the right partner, and then it was just calling around, and we knew we found the right place when I started describing the technology, and our partner, a manufacturing partner, said, "Oh, is that the thing with cesium on the inside?" Which, to my chagrin, I said, "Yes. How do you know about that?" And they had actually, in the much distant past, been contacted about producing thermionics before, and had actually done a lot of legwork on design and figuring out what type of materials they would have to work with years ago, which was pretty awesome. And then luckily for us, that project never went anywhere because it didn't have any government funding. That was kind of where we realized that we hit the nail on the head.
So Ian, so then I think we probably getting close to time. We get close to wrapping up. What are the immediate next steps for you and the team?
Yeah, the biggest next step is all the paperwork that goes along with actually taking money from people. There's way more than I ever thought there would be. So we're currently working on our LLC to C Corp conversion, all that stuff, setting up the board and whatnot. So that's the immediate next steps, and then once we get actually the cash in the bank, of course everyone takes like 2 weeks off for Christmas. So the biggest thing is at the start of the new year, we're gonna hit the ground running with working with our manufacturing partners and our actual product development people, making sure that we're basically going to start designing and getting ready to manufacture the minimum viable product, our basically demo unit that's going to go into the first power box and actually sit out in some kind of dusty field in a oil field someplace, kind of as our demonstration. And then from there, the goal is to actually start accepting purchase orders on units like that, so that we can hit the ground running with fulfilling those purchase orders with our manufacturing partners, and then we can work on scaling up from there. And that's our goal for about the next 6 months or so. And we think, given the success and reliability of our manufacturing partners, we're going to hit small production volume by the end of 2020, and then start looking into actually other products, other application spaces, and things like that with a full-fledged business development person at the beginning of 2021.
All right, I lied. You said something in there that sparked another question. So if one of the big competitive differentiators for this technology over existing technology is durability, how long do you have to leave your proof of concept or MVP box out in a dusty field before you've got enough data that proves that out? Like, will purchase orders come in when it's been out there for a month, or will people need to see it out there for 12 months? Or what does that need to look like, do you think?
You were very good at guessing your own answers to your questions. Yes, 1 month is what we've been told. 1 month is a good bar to set for just showing that it works out in the field, and then people will have at least some confidence in it. Yeah, we actually obviously asked that question right off the bat, because if they want to see a 10-year validation test, then obviously we can't do anything about that. But yeah, as I said before, the incumbent technology can fail at like any given time. They've actually had some of the devices fail in under a month. So if we can show nonstop steady state operation in the couple of weeks to month-long time frame, and then we'll just keep that one unit like up and running so that as time goes on, we'll have consistent validation for longer time scales, then yeah, that's the goal. But like I said before, one of the big things that we get to take advantage of is that the core technology itself has been tested for years at a time. When NASA and the Soviet Union were developing the technology, they were projecting 20 plus year lifetimes on the actual thermionic portions of the nuclear reactor. And so we've got a lot of data and history for some of that with thermal cycling. Obviously, we'll have to do all of that own work ourselves, but we're very confident in at least a couple year lifetime to start off with. And our main goal, I think we're going to target like a 7-year lifetime for the first product. But in order to get the interest and start taking purchase orders, the hard answer seems to be around a month.
Ian, if folks want to learn more about Atlas Energy Systems, or if they want to get a hold of you, what's the best way for them to do that?
Yeah, they can definitely go to our website, atlasenergysystems.org, O-R-G, not .com. .com is a Spanish boat manufacturer. And since we bought this domain as poor undergrads for $12 like 6 years ago, .org was the only one that was open. So we have that. And then my email is just simply my name, ian.hamilton @atlasenergysystems.org as well. And I'd be happy to talk with any interested parties or potential investors.
Ian, thank you so much. I really enjoyed it.
If you're thinking of launching a SaaS product, Startup Competitors can provide data on your closest competitors, survey potential users, or provide other product validation services. Learn more at startupcompetitors.com.